Bienvenido a un nuevo evento de Cátedra Europa.
Good morning. On the behalf of the 24th edition of Cátedra Europa, we give you a very warm welcome to the lecture Simposio sobre enseñanza de economía en el plegado, la propuesta de The Curriculum for Open Access Resources in Economics Core Project, for which we have the special participation of Felix Keck, research assistant from Universidad Técnica de Dortmund. Felix has finished his master's thesis at the Technical University of Dortmund in 2020. Afterwards, he started working as a research associate at the Institute of Energy Efficiency, Energy Systems, and Energy Economics. We'll now leave you with Felix. Felix, welcome to Cátedra.
Thank you, Fiorella, for your warm welcome, and welcome everyone to my presentation. I will just start sharing my screen real quick. All right, you should now be able to see my screen, right?
Yes, you can see.
Perfect. Okay, yeah, welcome again everyone to my presentation about benefits and challenges of grid forming inverter control in grid parallel operation as key to higher renewable generation penetration. I'd like to introduce myself first a little bit. Last year, I finished my master thesis at the Technical University of Dortmund, and I'm working now as a research assistant at the Institute of Energy Systems, Energy Efficiency, and Energy Economics, short IE3, of the TU Dortmund. My research fields are innovative controls in grids with reduced rotating masses, virtual inertia from converter interface generation, and of course, as per the title of my presentation, grid forming controls for renewable energy sources. So if we take a look at the power system of today, today's power system dynamics and behavior are mainly dominated by conventional generation. There is some renewable generation, as you can see here, illustrated by the PV power plant and the wind generator, but we cannot talk about massive integration today. The large rotational masses of the synchronous generators that we see here illustrated by these brown coal or nuclear power plants act like dampeners to the frequency disturbances. That is, if we take a look at the synchronous generators rotational frequency illustrated by these black phases, they are all directly coupled with the grid's frequency and very stiff coupled to each other. So they inherently dampen the effect of frequency deviations. If you imagine one of those phases deviating a little bit, it will be basically pulled back into normal operating mode by all the other directly connected synchronous generators. Conventional generation, however, is not interfaced directly or connected directly to the grid's frequency. It is interfaced with the power system due to power electronics. So the rotational frequency of this voltage phasor is basically an output of the control system. So renewable generation per se is not able to provide any inertia to the system. So what happens now if we integrate massively renewable generation into the system? So we replace old coal power plants or nuclear power plants with renewable generation without changing the controls of renewable generation as we know them today. To understand the issues that may arise out of this massive integration, we will first take a little step back and take a look at grid following inverter control in order to understand how these inverters work in the system in grid parallel operation. So here you will see a basic simplified inverter system consisting of a DC power source of some sort. Could be a PV power plant, could be a wind power plant, or anything else. Then we have a DC circuit with a DC capacitor. The main job of the DC capacitor is just to protect the DC source from the current ripple that is arising due to the switching of the valves in this inverter. And then on the other side of the inverter, we'll have the grid side, which is first interfaced with a filter, a sine filter, that usually is an LC or LCL filter, here now just illustrated by an inductor LF, a grid impedance Z, and the grid itself just represented with a alternating current voltage source here, U grid. So the grid following inverter control mainly takes place in a DQ rotating reference frame that is rotating at the same speed as the grid's voltage phasor. The way that we transform the momentary values, the ABC values IG, to these rotating reference frame DQ is we need a phase reference phi that we obtain by measuring the point, the grid's voltage UAC at the point of common coupling. And with a phase locked loop, we determine the phase reference phi that we use to transform these values to our rotating reference frame DQ. Then we will measure we'll have the measured current IDQ that our inverter is pushing into the grid. And the current controller basically compares this measured current with the current set point to determine the control deviation, and then mostly with a PI controller of some sort, calculates the control output, which is in this case UDQ, which is the voltage at the inverter clamps, but in DQ rotating reference frame. Then again, with the phase reference phi, we will retransform it to the UENV, U inverter, so the voltage in momentary values or ABC values at the inverter clamps that is needed in order to maintain this current set point. Then with the pulse width modulation, we calculate the switching firing pulses for the inverter's semiconductors. The vast majority of inverters that are at the grid nowadays is controlled like this or very similar to this. The main goal of controls that are designed like this is to maintain a current set point as fast as possible. That is because until now, the main goal was to inject as much energy produced by renewables into the grid as possible. So they are designed to have high efficiency and do not necessarily need to support the system stability at any time, because the system stabilization is taken care of by synchronous generators. Because of the increasing numbers of inverters in the system, at least in the European grid, that is what I know, we already have some kind of frequency and voltage support by inverters if they are of a certain size. But I will leave this aside now and talk about the general grid following control without these adaptations. So for this general grid following inverter control, we have no inertia or no fault current contribution. So if we take a look at this phasor diagram right here, we have the inverter's voltage, we have the grid's voltage, and between these two voltages, we have a voltage over the grid impedance, UZ, that is driving a current IG into the grid. So if we now face, let's say, a frequency deviation where the grid's voltage phasor is then rotating slower, the PLL will take care of this, and the current control will basically just compensate with also rotating my voltage, the U inverter voltage, slower. So we have basically no change or minimal change in the current that's been putting in the grid, because the inverter voltage will follow the grid's voltage with minimal control delay. So that is why it's called grid following inverter control. To come back to my question, what happens when we massively integrate these grid following controls into the grid? Well, first of all, because we now know how these grid following controls behave in case of contingencies or disturbances, we will have less inertia in the grid. So the grid is less resilient to disturbances. But also we will have synchronization issues. To illustrate why a massive integration of grid following controls will lead to synchronization issues, I've prepared a little test case. So first, I've simplified this small equivalent circuit that I had, so that I now just have an inverter here, a current source, which is representing the grid, and they are both connected via a grid impedance. So my first test case, the rated power of a converter is very small compared to the grid's short circuit power at the point of common coupling right here. So that is what I call a strong grid. And in my second test case, the rated power of the converter is not small So it's large compared to the grid's short circuit power at the point of common coupling. That is what I call a weak grid. So for a strong grid, that is what we expect. We have in blue the measured frequency as an output of our phase-locked loop. And in red, we have the real frequency. I've also incorporated a little frequency deviation here, an under-frequency event to show you that in a strong grid, in normal operation, a stable operation, we have a robust tracking of the grid's frequency, even in under-frequency situations. Whereas in a weak grid situation, the PLL is not able to lock the grid's frequency. So we are not able to follow the real frequencies that we have indeed at the point of coupling here, because the PLL will, the PLL's output here will look quite messy. It's able to follow somehow. You can see it here, but it's not very accurate. So that leads to wrong or invalid phase information. And we need this phase information for the DQ transformation in our controls. So the DQ transformative values should look in the strong grid a little bit like this, rather flat. In the weak grid, we have a lot of oscillations going on here. So we have invalid information about the grid's voltage phase. And if I try to control my system now with this invalid information about the angle that I have, I get a voltage output that looks pretty much like this, quite messy. Usually it should look like here in a strong grid, which are 3 nice sine waves interleaved with 120 degrees phase gap between each other. And here I have a lot of oscillation going on. That is because the PLL cannot robustly track the grid's angle anymore. One effect that is also enhancing this kind of synchronization issue is that in a weak grid, the current I inject with my inverter is so large that it impacts the voltage, or that it can impact the voltage at the point of common coupling. This information then is fed back into the control circuit and enhancing this effect. So taking all this into consideration, the massive integration of renewables right now is limited when using grid following inverters, because I can only incorporate so many grid following inverters before I face issues like I've shown here. That is why grid forming control has gained more and more attention in research lately. So I would like to answer you the questions now: what even are grid forming inverters? What am I talking about when talking about grid forming inverters? How are these grid forming inverters controlled? There are different ways of designing grid forming inverter controls. I will show you one of these ways in more detail and just name some of the others. How are grid forming inverters beneficial to the grid? And what are the challenges that we still need to overcome in order to integrate these grid forming inverters, at least in a sufficient amount to stabilize the grid without synchronizing asynchronous generators into the grid? So first, again, remember the attributes of grid following control. For grid following control, we have the angle generation by just measuring the voltage, and with the PLL, getting the phase reference for the transformation. The goal is to maintain the current set point, and as the voltage at the point of common coupling is basically just a result of the control, while the current that I push into the grid is the controlled entity, and we have 0 to none inertia when talking about grid following control. Now for grid forming control, it is basically everything just the other way around. For grid forming control, the angle is self-generated, so I have a constant frequency set point, and by integrating this frequency set point, I basically just get the phase reference I need for transforming my values into the rotating DQ reference frame for control. The goal is not to maintain the current set point, but to maintain the voltage set point at the point of common coupling. So the controlled entity in this system is not the current, but the voltage at the point of common coupling. The current that I push into the grid is basically a result of my control. So it's just the other way around when compared to grid following inverters. For grid forming inverters, when talking about inertia, we have adjustable inertia. How it is adjustable, you will see in a couple of minutes. So the basic control of a grid forming inverter looks like this. We still have our basic inverter system, which is just the same as for grid following inverters. So there are no hardware difference. We still have a DC source of some sort, a DC link, and an inverter here, again interfaced via a filter and the grid impedance with the grid. But now here we have the phase reference calculated by or self-generated with the constant frequency set point by integrating the constant frequency set point. Then, because the controlled entity here is UAC, the voltage at the point of common coupling, we measure this voltage, transform it with the self-generated phase reference phi into our DQ, synchronous rotating DQ reference frame, and feed this into our voltage controller. The voltage controller then compares this information, UAC DQ, with the set point, and then as an output generates the again the voltage that the inverter needs to be setting at the clamps in order to maintain the set point of the voltage here. Again, with a self-generated phase reference, where we retransform it into momentary or ABC values, the pulse width modulation will modulate the signal into switching firing pulses to control the inverter's valves. So, but with this control, grid parallel operation right now is not possible. This kind of control could be used mainly in off-grid applications or island grid applications, because the way I generate my phase reference here, I will have a voltage phasor that is basically anywhere and not at a particular point in comparison with the grid's voltage phasor. So I need some kind of synchronization technique. For the grid forming inverter, we can have synchronization dual-tube controller. The group controller is basically an F of P and U of Q controller. So it's generating the frequency set point here that was before a constant by measuring the active power that I put into the grid and comparing it with an active power set point. And it's generating the amplitude set point by comparing the reactive power I put into the grid with the reactive power set point. The way this synchronization technique works, it's also called active synchronization. I will explain briefly. When we take a look again at this phasor diagram, we have the inverter's voltage at the clamps. Then we have the grid's voltage phasor. Again, between these two voltage phasors, we have the voltage over the grid impedance that is pushing the current IG into the grid. So the current IG is dependent on the phase between these two voltages. So if, for example, the grid's voltage phasor is facing an under frequency, the phase angle between these two increases because now the inverter would rotate faster than the grid, leading to an increase in active power. This increase in active power will lead to a decrease in the frequency set point by the group controller. So basically my inverter will now rotate a little bit slower, and it will rotate slower as long as these two are asynchronous. As soon as they are synchronous again, it will have a stable operating point again at a lower frequency. Will probably oscillate a little bit around the frequency of the grid and then basically find its stable operating point again. With this delay of the droop control, or the delay of this droop controller is adjustable, and that determines my inertia. So you can imagine if I wait a little bit before resynchronizing with the grid in case of an under frequency event, I have increasing phase angle. I'll put out more active power, what is really good in case of an under frequency event. And when I wait a little bit before resynchronizing, I will have active power to support the frequency and then resynchronizing with the grid to maintain my operating limits again. The same mechanism again works also for reactive power in order to support the voltage. So if now not the phase angle between these two voltages change, but for example, we have an undervoltage event. The grid's voltage phasor is decreasing in amplitude. This will also have an impact on the voltage that is span across the grid impedance here, which will then again lead to a change in the grid's current. And then we'll have some reactive power be pushed inherently into the grid in order to support the voltage. So when I now compare grid following and grid forming inverters a little bit, I have for the grid following inverters again, the angle generation that is measured by a PLL, grid forming self-generated by basically integrating the frequency set point and synchronizing with the grid by the droop controller. The goal of grid following is to maintain the current set point, while the goal of a grid forming inverter is to maintain a voltage set point. The controlled entity for a grid following inverter is the current, while the voltage is just a result of the control. For a grid forming inverter, it's just the other way around. So the controlled entity is the voltage at the point of common coupling, and the current that is flowing is basically just a result. For grid following inverters, we have non-inertia, and now you also know why for grid forming inverters we have adjustable inertia. So this droop-controlled grid forming inverter is just one approach to design a grid forming inverter. It is quite similar to the traditional droop control in synchronous generators, just the other way around. In synchronous generators, we would have a P of F droop. So depending on frequency deviations, we will change our active power for primary reserve purposes. And it also has some weaknesses because the droop-based control, as I've shown with low inertia grids, the synchronization is not really trivial. There's also the synchronous generator-based grid forming inverter control. For this control, we have an accurate replication of synchronous generator dynamics. So we basically have all the equations of a synchronous generator in our control, calculate how a synchronous generator would act, and use this as an input to our inverter control. But with all these calculations, we also have numerical instability concerns and also no overcurrent protection. So that is something that we'll still need to add on top of this. Another approach to design a grid forming inverter is a swing equation-based grid forming inverter. It's basically a simpler mathematical model of a synchronous generator base where you just use the swing equation, so the main equation, if you want to say it like this, of a synchronous generator. And again, here we have no overcurrent protection, and we will face some power and frequency oscillations if not handled correctly. Another approach is the virtual oscillator control, which seems to be quite the robust mechanism, especially when it comes to synchronization with the grid. And it has shown superior grids, a superior speed during transients compared to droop-based. But it has shown some problems to meet specifications on amplitude and power injections. So now we already know what are grid forming inverters and how are they controlled. But now I'd like to talk about how are they beneficial to the grid and what are the challenges when interfacing grid forming inverters in a large amount or in a large multitude with a power grid. So first, we've learned that grid forming inverters are able to provide inherent inertia in order to support the frequency. The term inherent is here really important because opposed to inertia emulation, where the grid's frequency is measured and upon the rho curve, so the rate of change of frequency, the active power set point is changed. There we always have control delays. And this is also possible with grid following control, but inherent inertia, we have no control delays. This is something that's natural and is like the natural response of synchronous generators. So that happens without any control delay. That is here really important because it's not a fast primary reserve. It's basically an inherent response because of the way we set up the control. Then We also have inherent, again, very important, inherent fault current contribution to support the grid's voltage. Just remember the phasor diagram I've shown, where you could see how the grid's voltage would be supported in case of disturbances. We have a different synchronization method when compared to grid following inverter control. The grid following inverter control has proven to be not very accurate when interfaced with weak grids or low inertia grids. So this new synchronization methods might be more robust in weak grid scenarios, but there still needs to be proven in a way that we can securely interface these with the grid. And one other point is that these grid forming inverters, because they do not rely on measurements of the grid, are able to serve as black start units. So they have black start capability. And in case of a system restoration, they might also serve as kind of a fallback strategy for blackouts. So we could form local microgrids if there are enough grid forming inverters in geographically close location. We could form a local microgrid that is supported by these grid forming units, and then resynchronize the whole grid by resynchronizing these small microgrids. Well, this all sounds rather amazing and like the solution to all grid-related challenges. So why don't we just integrate a massive amount of these grid-forming inverters into the grid? Well, there are still a lot of challenges to be answered when talking about grid-forming inverters, and I'd like to show you at least some of these challenges or very interesting research topics that my colleagues and I are right now researching. So one has to do with the hardware limitations of a grid forming inverter or inverters in general. We still talk about power electronic devices, IGBTs, semiconductors that are inside these inverters, and they basically do not have any overcurrent capability. So if we take a look again at my favorite phasor diagram here, we see that, or we know that this the current IG that I push into the grid is depending on the phase. So if I experience a phase jump or an under frequency event, this will rise. But it can only rise until the inverter's rated current is reached, because these semiconductors can only carry their rated current and not more, or they will be destroyed. So in case of under frequencies or phase disturbances, a robust and transient current limiting is needed. Also, if I want to support the grid, providing inertia or providing more active power, I need a current reserve in order to be able to just support the grid. Because if I'm operating my inverter already at rated current, there's no excess current that I can provide because I'm already in my limits. I also have a limited short circuit capability, again, because of this overcurrent capability that is not really high compared to the overcurrent or short circuit capability of a synchronous generator that is up to 6 times their rated current. And all this yields that we need a transient current limiting just in order to operate this safely. One big challenge that we face when talking about this transient current limiting is that it needs to be really, really fast. So for example, if we take a look at this graph here, it's the current that I push into the grid, IG. We have the maximum current here. And when an event occurs, like a phase jump, the current will rise very fast. And I only know that the current, that there's a, that I'm facing a current overcurrent event at TF plus delta T, which is time for me to time for the current to rise, time for the current, time for me to register this event, and also time to activate my control countermeasures. And then it's already too late. At this point, the semiconductor controls might already be destroyed. So I need very fast transient current limiting. That is that have a fast impact on my current. And very important is I don't want to lose my grid forming capabilities about this transient current limiting, because one approach would be to change when I'm facing an event like this, to just switch the controls again to grid following controls. So then I have a grid following converter, which will basically just follow the grid's voltage phasor very fast and limit the current. But then we will lose our grid forming capabilities, which is not a problem if there's only one grid forming inverter in the grid and we still have a lot of conventional generation. But if we rely on these grid forming inverters to provide system stability, we cannot lose our grid forming capabilities. So that is one very interesting research topic that is discussed a lot right now. Another topic is the synchronization issues. For example, with active synchronization technique, there might be power oscillations between different grid forming inverters when I'm using a multitude of grid connected inverters that are synchronizing themselves with their active power exchange. So there again, a robust technique is needed. The virtual oscillator control might be one of the solutions of that, but we need to still look a little bit more into this. Another part is the active power reserve. So when I provide inertia to the grid, I have permanent active power exchange with the grid. On the right-hand side, you see a little graph here where the red graph is basically illustrating the active power exchange with the grid. It's always a little bit fluctuating. And at some points we have, for example, an under-frequency event where we have more active power exchange, or an over-frequency event where we have less active power exchange. So we will have to have reserve, positive and negative, so in both directions, to cope with the contingencies. Because what do these power exchanges do with our DC side? It's here in green, our DC voltage that is limited at a maximum UDC because of the isolation of our DC parts. And then there is also a minimal DC voltage that the inverter needs to operate and to be able to generate a nice sine wave for the grid. So we cannot go below this minimum or above this maximum. So there we need some reserve in between. But the energy storage in the DC circuit is very small. So a fast power increase of the DC power supply is necessary, because when we have here active power exchange with the grid, or provide more active power into the grid, this will draw current out of my DC circuit, which then will deload my DC capacitor, yielding a lower DC voltage. So that is why the DC voltage is X. And in order to provide more active power, I need a fast power increase of the DC power supply, because the energy stored in the DC circuit is so small. One way to do this, to increase the power supply of my DC into my DC circuit in case of PV parks, is the derated operation. So when I now take a look at the power curve of a PV power plant, and I see here the power P of the PV power plant and the UDC, so the voltage in my DC circuit, I'm not operating the PV power plant at the point of maximum generation, the MPP here, but at a derated operating point. When the system, the grid forming inverter, now is interfaced with an under frequency event, so it's exchanging more active power or pushing more active power into the grid, the active power will in the first moment be taken out of the DC circuit, leading to a decrease in the DC voltage. So the derated operating point will move along this curve to the left-hand side, which yields more active power generation of the PV power, of the PV plant. We need to be very careful here not to exceed this point, the point of maximum generation, because then this effect will just take into the opposite side. Then we will be somewhere here, and the DC voltage will then again get lower or decrease, which will also lead to less energy pushed into the DC circuit by the PV power plant, because we're on the left-hand side of the MPP curve. And that might be a destabilizing effect that we do not want. For wind parks, of course, we could also operate in derated operation, but wind parks have the perk that we have rotational inertia available. So when I take a look at this wind park, we have a synchronous generator here, we have a shaft, we have rotors that are rotating. So there is physical inertia, and one very interesting question here is, how can we use this physical inertia of a wind power plant? Traditionally, this is a wind power plant of the type 4, which means we have a synchronous generator that is fully interfaced. So we have a rotor side converter and a grid side converter with a DC circuit in between them. So all the power of the synchronous generator is flowing through these two converters into the grid. And traditionally, this grid side converter is operating in grid following mode. In literature, you may already find some frequency response-based virtual inertia methods, which basically means that the grid's frequency at the point of common coupling is measured. The ROCOF, the rate of change of frequency, is calculated, then fed into the control, where the active power set point is manipulated so that the whole machine will just exchange more active power with the grid. But this always has a lot of delays because I need to measure the frequency, which usually takes at least 1 or 2 cycles to have a safe or to have a valid measurement of the grid's frequency. And then again, this manipulated active power set point needs to run through the whole control in order to ramp up the production. Another inertia approach might be that this grid side converter is controlled in grid forming mode. So it is able to provide inherent inertia to the grid. And the main challenge here is, because I've shown that there are limits of the DC voltage, maximum and minimum limits that we may not exceed, so the main challenge is that we provide energy through the rotor side converter into the DC circuit fast enough to maintain the voltage in the DC link. If we are able to do this, we are able to tap into the physical inertia of a wind power plant. How this is possible is still an ongoing research topic. So now if we've answered all or answered some of these questions, there's still another question if we take a step back again and look at the whole system or the whole system level and see today's power system now interfaced with massive integration of renewables. There's still the question, do we need to put all these renewables into grid forming mode or just some of them? And in my opinion, there are just two main approaches. The first approach would be that all inverters are grid forming. It has some advantages. One would be that there would be less derating for each unit. So each unit would just have to reserve a small amount of power in order to stabilize the system. We would have less strain on each unit because the fault current contribution will be distributed along all grid forming units. We have a higher flexibility usage. So, for example, we could tap into batteries in home solar systems in order to provide inertia to the grid. And all of these units are black start capable. So that would be a very nice fallback strategy in case of a blackout. So we could easily build microgrids in order to restore a fully functional grid at a faster pace. Of course, this approach has much more complex synchronization and coordination than the other approach. The other approach would be that we only have a few grid forming inverters, but they should be quite large in scale. So this would be much easier to synchronize or coordinate. For this, the strategical placement is of paramount importance. It needs to be very precisely calculated where we place these grid forming inverters in the grid in order to maintain a stable system. Also, if we only have a few grid forming inverters, these grid forming inverters need to have a higher reserve. Speaking of current reserve and energy reserve. So these few grid forming inverters should only have then the sole purpose to support grid stability. Of course, there are also some mixtures of these two approaches or some approaches that lie in between these two. these two approaches possible. So now I've reached the end of my presentation. If you would like to engage in further discussions, you can find my contact info on the right-hand side of the screen. And well, now I'd like to thank you for your attention. And if you have any questions, feel free to ask.
Hey, hello.
Hi.
Hi, Felix. Thanks again. I wanted to thank you again for your presentation and for sharing this interesting topic with us. I wanted to ask maybe a question about the last thing you just presented about the two approaches that could be possible in your opinion. And so, yes, of course, maybe the first idea or the first logical idea would be to make all the inverters to operate in the grid forming mode. So if we consider maybe a large scale, it would really be like feasible that only a few of them operate in grid forming, and it can be just enough considering the limitations there are.
I'm sorry, I just didn't get the question.
I mean, in the second approach that you say that maybe only some of them could operate in grid forming mode, and not all of the inverters, for example, of a transmission grid. So, to what extent we can say that is possible, or that would be possible considered a high grid or a high transmission grid?
I think that depends largely on the way the future grid is operated. If we look at a little bit more into the future and we would have a grid that is operated 100% by inverters or renewables, I think we don't need that much inertia because for a power grid that we have today, we have slower controls and slower operate the system on a slower time scale, but a system that is operated 100% on renewables, we could basically just switch the frequency of all devices or have other shenanigans that are not possible today with synchronous generators because they are slow. And that is why we need to stick to this 50 or 60 hertz all the time. But for a system that is operated 100% by renewables, there might be just another way to operate it. So less inertia might suffice. So it might be possible to operate it with just a few. But as I said, the few grid forming inverters should then be larger scale and only operate as grid stability units or stabilizing units.
Okay, thank you for your opinion.
Yeah, and also it's if you want to incorporate it in a grid like today with still some conventional generation, it also depends on what other measures there are to stabilize the grid. If there are synchronous condensers or something like that also active. So if this inertia of grid forming inverters would only be for the first milliseconds, and then other units will take over that are just a little bit slower but have more reserve, then it's still less stress for the grid forming inverters.
Yes, okay. Thank you again. Well, I don't know if there are any more questions or...
Okay. We thank our guests for their special participation and all attendees for joining us in this section of Cátedra Europa. We invite you to continue supporting the education of talent students through our scholarship fundraising campaign, Más Becas, by clicking on the donation button on the homepage of Cátedra Europa. We also encourage you to stay connected to the rest of Cátedra Europa events. Thank you, everyone.